Hello everyone, welcome to another session in the deep learning series. We'll continue with the numerical example of sample neural network which we were calculating. So in the previous session, we completed the forward pass for the particular neural network. This is that particular neural network. We have completed the forward pass. The next pending this thing, the next pending this thing is backward pass or backpropagation. Now, what we do in the backpropagation is we are basically at the output stage, correct? Now we are basically moving from output to the second hidden layer, right? That is what this thing represents. So you are basically back propagating the error. You're moving from output to hidden layer 2, right? So consider this L1. Okay, L1 is basically this particular node, right? Over here you basically have three inputs, right? So you have K1 L1, K2 L2, K3 L3. So basically what you have to do is you need to back propagate the error. Okay, so conceptually back propagation is, I would say, it's nothing complex. You basically apply chain rule. So you apply chain rule and you basically calculate derivatives applying chain rule, and you basically update your weights. So conceptually it's similar to your linear regression gradient descent calculations, right? So over there, for updating weights, what you basically used to do was you used to take old value, right? Old value minus learning rate into delta, right? So that was your updated weights. Over here in back propagation as well, almost literally the exact same thing happens, but the only complex thing over here is you have huge number of weights to calculate, huge number of gradients to calculate. In linear regression it was only, say, one dimensional this thing. Over here you have, say, suppose you have a 3 cross 3 matrix, right? So if you have three nodes, you have 3 cross 3. This is again for one node, right? For one node you basically have basically 3 cross 3 matrix. But say in this you have only three nodes, and this network is basically of three nodes. Suppose you have a 100,000, suppose you have a 1,000 node neural network, right? So basically what you would do is you would basically be calculating 1,000 into 1,000, right? You would basically, so you would be basically calculating the 1,000 by 1,000 gradient matrix, right? So this is again for one node. The same concept would apply for 1,000 nodes as well, right? So I think that's why that's what is the major difference. But in general, but when you look at conceptually, it's the same only. So you're basically calculating your gradient. With the calculated gradient, you're multiplying your learning rate, and whatever output you get, you're basically subtracting it from your weight value, right? So yeah, so this is basically what is to be calculated for this particular node. So node or neuron, whatever people call it. I think node is more simplistic to follow. So this is all derivative. This is all delta for each of your weights, right? So for L1 it's K1 L1. This is similar to your weight matrix. The only difference is this is your delta matrix. Right? This is your derivative matrix. This is K1 L1, K1 L2, K1 L3, K2 L1. So yeah, this is your normal, and this is exactly the same as your normal weight matrix. The only thing what you basically calculate is you basically calculate change in weight from K to L neuron, right? Change in weight from K to L neuron. So how do you calculate that? Is you basically calculate. So over here, what is your output? Your output is error, right? So you basically take the derivative of error with respect to weight. So this is where your chain rule, this is where your concept of chain rule comes in, right? Since you cannot directly take value of your derivative of error with respect to weight, what you basically do is you break up the derivative. You break down the derivative into, so error into derivative of error in respect to output, right? Into derivative of output with respect to input, and input with respect to the weights. Basically what would happen, these two would get cancelled, these would get cancelled, so you basically would end up with the same thing. This is what basically is chain rule, right? Yeah, so this is where application of chain rule is in calculating derivatives in backpropagation. Again, you have bit of since we'd be using all of this, I'm just calculating derivatives of everything in the beginning only, of every activation function in the beginning only. This is your sigmoid. So we did see in that particular activation function aggregation different types of activation functions and their derivatives. This is more or less that only. This is ReLU, derivative of ReLU. Next you have softmax, derivative of softmax. Nothing new, it's the same only. It's more or less the same whatever was discussed in that particular page, right? So yeah, so what is the task at hand? The task at hand is fairly straightforward, right? And I think maybe equation wise it might be a bit too much to look at, but task is actually fairly straightforward. You calculate derivative of your error with respect to output first. Next, calculate derivative of output with respect to input, and input with respect to weight. Right? You basically need to calculate 3 derivatives. Now let us calculate the first derivative of error with respect to output. Oh yeah, basically what would happen is, now you know your errors, correct? Your error is nothing but your cross entropy, correct? Now you basically, what you do is this is what is your cross entropy. Now you basically calculate this particular value, right? So when you actually go into this particular, since you have a positive sign, you can take individual derivatives. Derivative y is a constant, keep it aside. Log of x is, say, since you're taking derivative of o out 1 and o out 1 is the value, so it's nothing but log of x. Derivative of log of x is 1 by x. Then since 1 plus y of minus 1 is constant, you keep it aside. And derivative of 1 minus o out 1 is nothing but 1 by 1 minus the value. So this is derivative of error with respect to your input, error with respect to your output. So one advantage of this is, since all of these error notations would change, correct? You have calculated over here for the first node or first neuron. Now for the other 2 nodes, it's the same, this thing is the same output only. The only thing which needs to be changed is the notation. So you're calculating the y1, here it would be y2, here it would be y3, right? So you need to make similar changes across other equations as well, right? So this is your first derivative calculation, derivative of error with respect to your output. The next this thing what you need to calculate is derivative of your output with respect to your input, right? So your output is nothing but your sigmoid activation function, your softmax activation function is basically what is your output, and you have your input, right? Now basically what you do over here is so this is, again, since you have exponential this thing, you would basically take similar derivatives. So if you basically take you basically move this top, right? So it will become e to the power of O(n) square, then O(n)(1), O(n)(2), O(n)(3). So since so the derivative would be O(n) square, because this whole thing, if you assume this as x, correct? So into x to the power of minus 1. If you consider the whole thing as x, so it becomes x power minus 1 is minus 1 into x square. So this is O(n)(1). O(n)(1) is basically a constant. Then this will be O(n)(2) plus O(n)(3), right? So in a similar manner, you would be calculating your derivative output with respect to input. You would get similar values as well. So that's what you over here, right? You basically need to just take the whole denominator as x. I think all of this is sort of basic derivatives concepts. So you basically take the whole thing as x, pull it above, it will become x to the power of minus 1, right? So derivative of x is nothing but n into x to the power of n plus 1, n minus 1. In this particular case, it becomes square, it goes to the denominator, so it basically would have a minus 1 at the end. Yeah. So the remaining this thing, next is derivative with respect to input with respect to each weight. That derivative is basically pending.